Hello. Today I'm going to show you how to solve a curved beam stress example, how you can compute the stress of in a curved beam. The example I have here is a hanger made of ASTM structural steel bar with a square cross section with 10 millimeters on the side, and the radius of curvature is 150 millimeters to the side surface of the bar. And what we're looking for is the load F that will cause yielding of the steel. Curved beam have many examples. One of the examples is designing hangers. We have straight beams and then we have curved beams. One of the main differences between curved beam and the straight beams is that for curved beams, the neutral axis does not go through the central axis of the beam. That causes a main difference in a stress computation. The relationship we have for computing stress in curved beams is sigma r equals m theta capital R minus R over A R RC minus R. In this relationship, this capital R is the radius to neutral axis, and RC is the centroidal radius, the radius to centroidal axis. The R is the position of your desired location, where you're actually interested in computing the stress for. And A is the cross-sectional area. So C indicates centroid. Now, what we're interested here is to determine the load that will cause yielding of this steel. The first thing we need to do is we need to go look at the handbook of mechanical engineering and find the material ASTM A36 structural steel bar, and then for that material we need to find the yield stress, because our goal is to find the corresponding F. And once you have consulted a mechanical engineering handbook, you will find out that for the ASTM A36 structural steel bar, the properties are sigma yield, or we can call it, sigma yield is 248 megapascal. So our goal is to find R such that sigma R goes to sigma Y, and then relate that sigma R to this F. Essentially, for any cantilever beam with an end load, the crucial section for normal stress due to bending is right at the support, meaning that here. The difference between this beam and a straight beam is that for the straight beams, the cross-sectional area is parallel to the wall. All right, so we need to transfer this force to this section and then compute its corresponding moment. Our desired section is this section, we transfer the force from this point F to this point with its coupling moment. And the moment would be this moment. We use the principles of statics, and then we transfer the force from this point or this point to this point. This point. At the centroid of the desired section where maximum moment occurs. Maximum moment corresponds to maximum stress, and then we can set that maximum stress equal to sigma yield. This distance from F to the centroid of the desired section is the total distance, let's call it D, minus B over 2, and B being half of this length. This was B, and we are looking for excuse me for B over 2. So our D is 325 and our B is 10 over 2 over 5. Once we have our moment arm, we can compute the coupling moment. In this case, we are interested in neglecting the axial stress, meaning that once you transfer this force from this point to this point, you're going to have a compressive stress pointing down, and you have a coupling moment. We're going to ignore the uniaxial stress because of F, so we are going to ignore F over A. And we only consider the stress caused by coupling moment. If you're interested, you can easily add the other stress component to this stress, meaning that you can always compute sigma total equal sigma R plus sigma F. It's equal to sigma R plus F over A. I'm only interested in this part of this problem because it's more interesting. Otherwise, we can add the other part, which is very easy to add to the first part. All right. Now, for a curved beam with a square cross section, if you look at, for instance, tables, or you can compute it yourself, you can see that for curved beams with a square cross section, your R, the neutral axis, is going to be A over B ln RO over RI. RO being, RO is the outer radius, meaning that it's RI plus B. So RO is equal to, we had our RI was the radius of curvature to the inside surface of the bar was 150. So our RI was 150 plus 10. So our RO is 160. Then you can substitute this along with A, and our A is equal to B squared, 100 millimeters squared. Just note that you can find this R, radius of curvature, the radius to neutral axis, in various tables. For curved beams, it's not as easy and as straightforward as in straight beams, so you can look at tables and find that for neutral axis for a square cross-section curved beam, you have this relation. So once you substitute those numbers into this relation, you can find which is going to be equal to 154.946. And then once you have the radius neutral axis, you can go back to this relation. Sorry, and before doing that, what you need to do is you need to compute M max. For M max, we have the distance and we had the force. Our force is unknown, obviously. The distance is d minus b over 2. So it's F 325 minus 5, which is 320F. And you should note that our convention is mostly like, because this coupling moment is clockwise, my convention is, I assume it's negative. Once you have this moment and you have this R, you can substitute, let's call this 1, 2. So substitute 1 and 2 into this equation. Let's into sigma R. Now, one difference between curved beams and straight beams is that you do not know a priori that where the maximum stress occurs. So what you need to do is you need to always compute the stress for both inner radius and outer radius, inner edge and outer edge. So you compute always sigma O. So in this case you have 320F and there is a negative negative sign because it is clockwise. And then you have 154.946 R minus RO. For sigma O, R is equal to RO. And then you have 100 multiplied by 160 multiplied by 155 minus 154.946. And this RO was also equal to 160. And sigma O is going to be equal to 1 point. Once you do this multiplications, you get that it's 1.871 F. For sigma I, you do the same thing. You have minus 320 F, 154.946. This time it's minus 150 because R is equal to Ri equals to 150. Divide that by 100, 150, and 155 minus 154.946. And you get 1 minus 1.96, 1.9, I did write it down somewhere, sorry, 1.954. Then what you need to do is to compare the magnitude of these two numbers, the absolute values, and you see that once you compute this, sigma max is going to be sigma I. So sigma max is equal to sigma I equals to 1 minus 1.954 F, right, equals to, and there is a unit here because it needs to be the stress unit, same unit as a stress, so millimeters squared. And this sigma max needs to be equal to sigma y to cause yielding, and sigma y was minus 248. And why is it minus 248? Because we are talking about the inner radius of this, or inner edge of this curved beam. It's under compression, so it's minus 248. This gives us F being equal to minus 248 over minus 1954, and it should give you something like 126 Newton. So if you apply 126 Newton, this will cause yielding in inner edge of this curved beam. Hope you have enjoyed this example. I'll be back soon. Thanks for paying attention.